Three-phase induction motors are very popular because of their simple, robust construction and high reliability. Let's understand the construction of induction motor. There are mainly two parts in an induction motor: stator and rotor. Stator. It is made up of number of stampings in which different slots are cut to receive three-phase winding, which is connected to three-phase AC supply. The three-phase windings are arranged in such a manner in the slots that they produce a rotating magnetic field after AC supply is given to them. Usually, windings are kept at different pitch circle. The windings are wound for a different number of poles depending upon the speed requirement, as speed is inversely proportional to the number of poles, given by the formula Ns is equals to 120 F upon P, where Ns is equals to the synchronous speed, F is equals to frequency, and P is equals to number of poles. Rotor. Rotor consists of cylindrical laminated core with parallel slot that carry conductor bars. Conductors are heavy copper or aluminum bars which fit in each slot. These conductors are braced to the short-circuiting end ring. The slots are not exactly met parallel to the axis of the shaft but are slotted a little skewed for the following reason. Number 1. They reduce magnetic hum or noise. Number 2. They avoid stalling of motor.
Types of three-phase induction motor rotor. Three-phase induction motor have two types of rotor. One is squirrel cage rotor and second is wound rotor. Squirrel cage rotor. This is the squirrel cage rotor of three-phase induction motor. There are two types of three-phase induction motor rotor. One is squirrel cage rotor and second is wound rotor. About 80 to 90% of the rotor are squirrel cage rotor. It is simply consists of copper bars and metal ring. Each slots consists of copper bar. These copper bars and end ring are short-circuited. Also the bars are slightly skewed for starting purpose or to decrease locking. Wound rotor. This is slip ring type or wound rotor three-phase induction motor. Wound rotor is the type of three-phase induction motor rotor. About 10% induction motor are wound rotor motor. It basically consists of laminated core and slip ring and copper winding. The slip ring is connected to external resistance. Speed control of three-phase induction motor via rotor resistance control method is possible with this rotor.
Consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But, at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor.
Close the main switch to start the motor on no load. Observe the direction of rotation of the motor, say, looking from the left-hand side of the terminal box. You notice that the motor shaft is rotating in the clockwise direction. Measure the RPM with a tachometer. Open the switch. Interchange the connections of any two input supply terminals of the motor as shown. Start the motor once again. You can now see that the motor shaft is rotating in the anti-clockwise direction. You check the RPM again. You can see that the speed obtained is the same as in previous case. You have succeeded in reversing the direction of the motor. You have practically seen how to reverse the direction of rotation of a three-phase induction motor.
Speed control with respect to stator side of the induction motor. Speed control with respect to rotor side of the induction motor. The speed control of induction motor by considering to control on stator side can be also subdivided into several speed controlling methods such as by changing the supply voltage of the motor, changing the stator pole numbers of the motor, changing the frequency of the supply side of the motor. By changing the supply voltage of the motor, as can be seen from equation, the torque developed by an induction motor varies as square of the voltage applied to its stator terminals. Thus, by varying the applied voltage, the electromagnetic torque developed by the motor can be varied. Changing the stator pole numbers of the motor. The primary factor in determining the speed of an induction motor is the number of poles, given by the below formula. Here, Ns is synchronous speed in revolution per minute, F AC power frequency, P is number of poles per phase winding. Formulation: changing the frequency of the supply side of the motor. By changing the supply frequency, The motor synchronous speed can be altered and thus the torque speed of a three-phase induction motor can be controlled. The synchronous speed of the motor at rated condition is known as the base speed. By using variable frequency control, it is possible to adjust the speed of the motor either above or below the base speed. Increase in frequency increases the torque speed relation, and a decrease in frequency decreases the torque speed relation of the motor. The speed control of induction motor by considering to control one rotor side can be subdivided into several speed controlling methods such as adding an external resistance into rotor side circuit, applying cascade connection, injecting EMF into rotor side circuit of the motor, adding an external resistance into rotor side circuit. This method is applicable only the wound rotor induction motors. Speed variation can be obtained by inserting external resistance in the rotor circuit. External resistance are placed in series with the rotor winding during starting to limit the starting current. Without the external resistance, the starting currents are many times to rated currents, depending on the size of the machine. It can down 300% to over 900% of the full load current. Once the motor is started, the external resistance can be cut out to obtain high torque throughout the accelerating range. Applying cascade connection. In this cascade operation method of induction motor speed controlling, there are two motors are mounted on the same shaft of the motor and run at same speed. One motor is connected to three-phase supply and other is worked from the field-induced EMF to the first motor through slip rings. By using this method, different speed can apply for induction motor and speed can control, injecting EMF into rotor side circuit of the motor. In this induction motor speed control method, external voltages add into the rotor circuit of the motor and the frequency must be same as slip frequency. So injecting EMF in opposite phase of the rotor increase the rotor resistance. By that, this method can be used to speed controlling of the induction.
As we know, the speed of induction motor can be controlled in many types of ways. In this video, we will see how the induction motor can be controlled by using direct torque control or DTC method. We will perform the controller by using the D-space system, but first of all, we will use the MATLAB to design the DTC control to be implemented in D-space system. This design we will use the simulating block instead of doing codings to make it easier to be used. After the design is complete, we will start build up through the D-space and it is ready to be used.
as a power source of the entire industry. Motor has shifting the interchange between electric energy and kinetic energy by interaction between electricity and magnetism. It's widely used by its simple structure, low cost, and durability with high efficiency and reasonable performance. Nowadays, motor plays a dramatically important role in the global automation industry. It has great recognition at the metallurgy, electrical power, petrochemical, coal, mining, building materials.
Subdivided. Number 1 electrical faults. Number 2 mechanical faults. Number 3 environmental faults. Electrical faults. These faults are further subdivided into 7 types such as single phasing fault. Single phasing fault is occurred when any one phase of supply voltage is getting lost, because 3 phases voltage supply is must require for normal working of 3-phase induction motor. Due to this fault the motor could be burned or heat up. Reverse phase sequencing fault. Reverse phase sequencing fault is occurred when any one phase of 3-phase voltage supply is reversed. Means the phase order of supply voltages are swapped. Due to this fault the direction of rotation of motor has changed. Under or over supply voltages fault. This fault is occurred when supply voltages are under or over the specific limit. The limit of 3-phase AC supply voltages is 380 to 440 volts. So when supply voltages are crossed this limit, then motor could be burned or heat up. Mechanical faults. Mechanical faults are such types of faults which are generally occurred in internal housing of 3-phase induction motor. These faults are further subdivided into 3 types such as broken rotor bar fault. The squirrel cage induction motor consists of rotor bars and shorted end ring. If these bars are damaged or partially cracked, then this type of fault is called rotor broken bar fault. There are so many reasons for occurring this fault, but it has mainly observed that this fault is occurred due to manufacturer defect. Because during brazing process non-uniform metallurgical stress may occur in rotor bars which may lead the rotor bars failure during the rotation of rotor. Broken rotor bar fault is shown in figure. Rotor mass unbalance fault. If we concentrate on the construction of induction motor, then we can easily know that the rotor of induction motor is placed inside stator bar, and it rotate coaxially with stator. In heavy motors, it is centrally aligned with stator, and its axis of rotation are also same with the geometrical axis of stator. So the air gap between inner of the stator and outer of the rotor is same. Similarly, if this air gap is not same, then the situation which is referred to eccentricity would be occurred. In this eccentricity situation, the rotor fault would be occurred, that is called rotor unbalanced fault. Bearing fault. In 3-phase induction environmental fault. In 3-phase induction motor different faults could be occurred simultaneously, and, in these faults, environmental fault is also so much important. Induction motor surrounding environment such as ambient temperature and moisture etc. affect on the performance of induction motor. These factors reduce the performance of induction motor. Beside this, the vibration in induction motor that could be due to any reason such as not properly installed also affect the performance of induction motor. So during the installation of 3-phase induction this factor should be kept in mind.
There are 3 types of motor maintenance. Preventive motor maintenance is maintenance that is done on a routine basis in the field with no disassembly of the motor. The purpose of preventive maintenance is to maintain the motor, clean the exterior parts, lubricate accessible parts, make minor adjustments, and identify potential problems. Periodic motor maintenance is maintenance that is done on a regularly scheduled basis, usually in a shop after disassembling the motor. The purpose of periodic maintenance is to run tests on the motor, clean the interior, and inspect and lubricate parts. Corrective motor maintenance is maintenance that is done as needed to correct problems that were identified during the preventive and periodic maintenance checks. Select Next to continue. Preventive motor maintenance is the easiest type of maintenance to do. The primary purpose of preventive maintenance is to maintain equipment in good operating condition. Preventive maintenance is conducted on a routine basis. Routine basis can mean daily or weekly or at any other short-term interval that is appropriate for the equipment. Preventive maintenance generally is done in the field. That is, the equipment is not removed from its location. No disassembly of the motor is required. Preventive maintenance usually does not require the equipment to be taken out of service. However, at times it may be necessary to tag out the motor from the power source. Select Next to continue. Inspection is a very important part of the preventive maintenance program. By routinely inspecting equipment, you can determine if the equipment is operating as it should. If the motor is not running, begin your inspection by looking over the equipment, examining its general condition. Visually inspect the motor for any loose fastenings or broken parts. Check belts and pulleys to ensure that they are neither too loose nor too tight. Be alert to any wearing or fraying. If you find problems, tag out the motor in accordance with facility guidelines and make these minor adjustments. Inspect the motor for overall cleanliness. Look for dirt, dust, and grease, or anything else that blocks the motor's screens and vents. Inspect lubricated areas of the motor, such as the bearings, for evidence of leakage and dripping. Visually check oil levels. If possible, start the motor to find out if it comes up to speed in the normal amount of time. Select Next to continue. Another critical part of a preventive maintenance program is measurement. Measurement allows you to accurately assess the functioning of various aspects of the motor. These aspects include current, temperature, and vibration. To determine if your equipment is functioning properly, it is not enough to take measurements alone. When you take measurements, you must compare them to previous measurements in order to track equipment performance. Over a period of time, measurement records will indicate if trends exist in the functioning of the motor. Such trends can reflect a gradual deterioration in a specific area of the motor. In order to make accurate comparisons, measurements must be taken in the same place time after time. Select Next to continue. Areas that call for cleaning and lubrication should be attended to at once. By taking these routine maintenance actions, you'll ensure continued efficient operation of the equipment. If the motor is not operating, use a vacuum cleaner to clean the exterior of the motor to remove dirt and dust from the vents. If the motor is operating and your facility allows the use of low-pressure air in cleaning, direct the airflow through the motor to remove dust and dirt from the vents. This procedure will keep you away from moving parts during operation. Select Next to continue. Motors are disassembled by starting from the ends and working toward the center. When disassembling a motor, use techniques that will protect both the motor and yourself, and that will make the reassembly job easier. Begin disassembly of the motor by match-marking the end bells and stator housing to provide reference marks for proper end bell replacement later. Remove, bag, label, and store the bolts. Remove one end bell. Use a piece of wood or rubber mallet to help set it free. As you remove the end bell, take care so the rotor does not drop and damage the stator. Rotor removal is a very precise operation. It may take 2 people to do it. Make sure the clearance between the rotor and the stator is even on all sides and at both ends. The rotor must be properly aligned to prevent damage to the rotor or the stator windings as the rotor is removed. Set the rotor aside on a clean, soft surface where it will not be damaged or roll. Inspect the bearings according to the manufacturer's instructions. Replace the bearings as necessary. Remove the other end bell. Select Next to continue. Once you have disassembled your motor, you're ready to inspect and clean the parts. Wipe the end bells with a soft, lint-free cloth. Inspect them for cracks and other signs of damage. Check the bearing seating surfaces of the end bells to determine if they are out of round, tapered, or worn. Inspect the shaft and bearings for signs of damage. If the bearings are bad, they will need to be replaced. Inspect the rotor for loose or broken bars, end ring damage, and overheating. Inspect the rotor fins for signs of damage. Once you have inspected the rotor, clean the rotor and stator with a soft lint-free cloth and approved solvents to remove dirt buildup that may hide problems. Take care to prevent damage to the windings and to prevent loose dirt from being rubbed into the winding, as this can reduce insulation resistance. After cleaning the stator, inspect the windings for discoloration and signs of abrasion. Inspect the pole pieces for scraping, rubbing, or overheating. If you detect any problems during the cleaning and inspection process, inform your supervisor.